This video is about deriving surface consistent residual statics using the surescsv program. It also shows how to apply those statics using the sushiftcsv program. This video makes considerable use of shot stacks and receiver stacks to show results. If you do not know what surface consistent statics are, or you do not know what shot and receiver stacks are, you should see my video about the SU Stack Up program.
Extensive examples and tests for SU-res-CSV and SU-shift-CSV exist in Demos Geom3D, SU-res-CSV, Demos Geom3D, SU-shift-CSV. The Geom3D SU-res-CSV scripts create a fake 2D survey and a fake 3D survey, and both use SU-res-CSV and SU-shift-CSV somewhat realistically. In fact, the fake seismic traces in this video are modified from the traces created using the scripts for the fake 2D survey in Geom3D SU-res-CSV. The Geom3D SU-shift-CSV scripts are unrealistic tests of various options. Display of some shot gathers of fake 2D survey after mute. Display of some shot gathers of fake 2D survey after NMO correction. Note that the traces of this shot are all shifted relative to other shots. This is what a surface consistent shot static looks like. Some traces also have surface consistent receiver statics. Of course, it is easier to see surface consistent receiver statics if the traces are sorted into receiver gathers, as done here. Naturally, we still see surface consistent shot statics in those receiver gathers. Next, I show shot stacks, receiver stacks, and CDP stacks of this fake 2D survey. Shot stacks are stacks of all traces of the same shot. Receiver stacks are stacks of all traces of the same receiver. In simple situations, shot and receiver stacks clearly show surface consistent statics. For more information on shot and receiver stacks, see my video about the SU Stack Up program. Shot stack before using SU-res-CSV to determine statics. Each trace here is a stack of all traces of one shot. Shot-to-shot static differences can clearly be seen. Receiver stack before using SU-res-CSV to determine statics. Each trace here is a stack of all traces of one receiver. Receiver-to-receiver static differences can clearly be seen. Part of CDP stack before using SU-res-CSV to determine statics. Setup of SU-res-CSV to determine surface consistent statics, and setup of SU-shift-CSV to apply those statics. The statics are output from SU-res-CSV in default files sstat.csv and rstat.csv. The statics are input to SU-shift-CSV in files with the same default names. We will see those files later, but next we look at the results of the stacks. Shot stack after applying statics from SU-res-CSV. Receiver stack after applying statics from SU-res-CSV. part of CDP stack after applying statics from surescsv. Shot statics file stat.csv is shown above. This is a Q file which can be used by other programs, not just sushiftcsv, and also easily input into spreadsheet programs such as LibreOffice Calc. By default, surescsv uses shot identifier key FLDR and statics key sstat, which you can see in the CSU header records above. The sstat values are the long numbers at the ends of the Q records in milliseconds. This shot statics file also contains SX, SY, num1 sstat, and num2 sfold values. The num1 and num2 are just prepended because of some Q record standards. The num2 sfold is the number of traces of each shot which were used during the last iteration of surescsv analysis. See parameter documentation at the end of this video. The num1 sstat is the value of sstat from the first input trace of each shot. It is not used at all within surescsv. It is output in this file because it might help produce a floating datum in certain situations. I plan to produce a separate video about floating datum. Receiver statics file rstat.csv is shown above. It is very similar to the sstat.csv file. By default, surescsv uses receiver identifier key gaps and statics key gstat. Note that in both files the first line contains numid, average, long wave, use off, I use off, and then their values. Except for average off, these are parameters. The average off value is the average offset of all traces in the input dataset. Several of the other parameters default their values based on this average offset value. See parameter documentation at the end of this video or from surescsv itself. So, how does surescsv derive statics? It does so using a variation of the power stacking methodology described by Ronan and Claerbout, Geophysics Volume 50, 1985. The surescsv documentation describes it as follows. Conceptually, the basic methodology is store all input traces, they should be NMO corrected, stack all traces into their CDPs, cross-correlate each trace of a shot with the stacked trace that has the same CDP number. Sum those cross-correlations for each shot. Find the time of maximum of cross-correlation of each shot. Perform a 3-point interpolation around that time using the neighboring correlation values, yielding a fractional sample shift. By default, reduce long spatial wavelengths in shot shifts. Restack the CDPs with the derived shot time shifts applied by the inst8r routine, which is able to perform fractional shifts. Repeat the procedure above, but for receivers. That is, cross-correlate each trace of a receiver with the stacked trace that has the same CDP number, and so on. Repeat everything above for the amount of iterations you choose. Output the shot and receiver in CSV files. It is much easier to understand visually. Remember this display of some shots? First, all traces are stacked into CDPs internally. Then, all traces of this shot are cross-correlated against the CDPs they stacked into. The time of maximum sub-cross-correlation is found and interpolated for more accuracy. Then the same thing is done for this shot. And the same thing is done for this shot. And the same thing is done for this shot. And the same thing is done for this shot. and the same thing is done for this shot, and so on for all shots in the data set. Okay, remember that the CDP stack looked like this? Well, it looks the same internally on the first iteration inside surescsv. This means that only one of the shots shown previously has a large shift relative to its CDPs. The shifts for all shots are stored internally. Conceptually, those shot shifts are then applied to all stored traces, and a new CDP stack is made internally. The receivers now all undergo the same process using the traces after shot shifts. Traces of each receiver are cross-correlated against their CDPs in the new CDP stack, and their shifts are determined. All receiver shifts are also stored internally. Conceptually, these receiver shifts are then also applied to all stored traces, and a new CDP stack is made internally. The shots are processed again, and any new shift value is summed into the stored shot shifts. Then a new CDP stack is made again, and the receivers are processed again, with any new shift value summed into the stored receiver shifts, and so on until final iteration. I say conceptually because repeated shifting of traces would degrade them. Instead, the raw stored traces are always reshifted by the current total accumulated shot and receiver shifts during CDP stacking and cross-correlation. Now, a slant is added to the fake 2D survey to show how surescsv reacts. Shot stack before using surescsv to determine statics. Receiver stack before using surescsv to determine statics. CDP stack before using surescsv to determine statics. Shot stack after using surescsv to determine statics. Receiver stack after using surescsv to determine statics. CDP stack after using surescsv to determine statics. Note that the shot and receiver shifts are still derived, but the slant remains. That is what surescsv is supposed to do. The surescsv program cannot determine long period statics. A slant is a very long period. The reason that surescsv cannot determine long period statics is that it is comparing shots and receivers only with the CDPs into which they stack. It is complicated to compute the maximum wavelength static that can be determined. For simple 2D surveys, a good rule of thumb is approximately the shot spread length. If you believe that your survey has long period statics, then they should be removed using refraction, first break analysis, uphold times, and or near surface modeling. Determining whether a slant is statics or structure is not a job surescsv can do. There are several parameters which modify the iterative solving technique explained previously. The long wave parameter averages derived shifts of shots near each individual shot and subtracts that average from each individual shot. And it averages the derived shift of receivers near each individual receiver and subtracts that average from each individual receiver. This occurs after processing the shots for each iteration and also after processing the receivers for each iteration. This reduces long period artifacts that might be induced in the derived statics due to incorrect animal velocity correction, geometry spread artifacts, structure, noise, and so on. Parameter use-off is best explained while looking at the trace of some input shots. Note that this shot is different. It is not located in the center of its receiver spread. This means this shot has some traces with larger offsets than neighboring shots. If the animal velocity correction is not perfect, these traces will not align well with their CDPs. So, the summed cross correlations will find an incorrect amount of shift for this shot. Parameter useOff defaults to using a limited offset range rather than all offsets. This means all shots and all receivers have a more consistent set of traces during analysis. So, animal velocity inaccuracies and similar issues have less influence on the results. Of course, this also means that less traces are used during the analysis. So, for noisy data, you may want to reset useOff to use all offsets. Finally, note that surescsv and sushiftcsv will function for 3D surveys. An example setup follows. Tests using a fake 3D survey exist in Jum3D surescsv. Note that the receivers are uniquely identified by two keys, groaners and gaps. By default, these keys are set by sugeom.csv to line and point numbers from SPS2 files. The shots are still identified by default key FLDR, but the CDP identifier is keys IGI and IGC, which are set by the 3D grid program subin.csv, and the cdivider parameter is set to 3.4. The cdivider parameter bundles multiple CDPs together to reduce decoupling. See parameter documentation later. The documentation for these programs is included next, just so you can read it here conveniently. I remind you that the program documentation can change after this video.